Now let's look at mass spectrometer. Mass spectrometer is one of the popular concepts, right? At our introductory level, we need to actually know about it and be able to do calculation around mass spectrometer. So one of the common concepts around this that we need to know when we come to mass spectrometer is understanding relative abundance. Let's see how it is connected to atoms so that we can calculate that. So we say an atom, right? So we have elements here, and we say element is, what's that writing? So element contains atoms, right? So element contains atoms. So let me call this in atom 1, atom 2, and then atom 3. This is the relationship, right? Where can we find elements? We can find elements on the periodic table, and each element contains atoms. It can be 1, 2, 3, 4, 5, right? So element contains atoms. All these atoms of the same element, we call them isotopes. So these guys are the isotopes. We define isotopes in some sessions already. So isotopes are atoms of the same element having the same atomic number but different mass number due to difference in their neutron numbers. We'll talk about that. So if you take a critical atom for this guy, let's say this is an element of atomic number 6. So I'm going to say carbon. So let's say this is carbon, the element is carbon, and carbon alone has isotopes. We have carbon. So carbon is actually having atomic number of 6. So all of these children, or all of these atoms have carbon 6, but then here is atomic number 12, atomic number 13, atomic number 14, right? Mass number. This is mass number. So mass number 12, mass number 13, mass number 14, atomic number 666, because they are all belong to the same element. So this is the element carbon, and these are the atoms of the element, and all these atoms together, they form isotopes. That's what we define isotopes are. So you have a picture. So if you have a basic thing like that, so I'm taking carbon 6, carbon 12. So we call it carbon 12 because we know it's a carbon, and all carbons are having atomic number what? 6. Mass number is 12. So the mass number is the different one. So we got this one, we'll call it carbon 12. We call this one carbon 13 and call this one carbon 14. So we are calling them based on their number of, all of them are carbon because they are all children of the element carbon. But then if you want to identify one atom of the same element from the other, you have to mention the atomic number. So carbon 12 is that carbon atom with atomic number 6 and mass number what? 12. Carbon 13 is that element, that atom of carbon, right? That has atomic number 6, mass number 13. Carbon 14 is the one that is we are having mass number 6, mass number 14, atomic number 6 as well. So carbon 12, carbon 13, carbon 14. The same thing will apply to oxygen 16, oxygen 18. The same thing will apply to chlorine 37, chlorine 35. Right? So all these are atoms of the same. So elements contains atoms, and all the atoms together we call them isotopes. The relationship between the atoms is isotopy. So they are isotopes. Okay. So now I have a scenario for you over here. So if you fetch a cup of carbon or a spoon of carbon, just like how we have it over here. So here, let's say we just have a scoop of carbon. So these things, I know is salt, right? So I want you to have the analogy. That's why I'm bringing this picture for you. So you have a spoon of, like we just fetch an element. We fetch this powdery from, so like something in this way, then we fetch it, right? When we fetch it, we're able to have this. We just fetch. So, but we know that this is carbon that we fetch. We need to know that carbon is an element that contains various atoms, right? We have atoms, carbon 12, carbon 13, carbon 14, for example. So these various isotopes, the one we fetch doesn't mean that the scoop that we have contains only carbon 12. It doesn't mean that it contains only carbon 13. We know they are all carbon, all right. We fetch carbon, all right. But then we don't know the amount of carbon 12 inside. We don't know the amount of carbon 13 inside, the amount of carbon 14 inside, right? So yes, so if you have a scoop, a sample, so we say using the word sample now. So if you fetch a sample of carbon, does not necessarily mean that you have carbon 14 to our carbon 12 to our carbon 13 to our, it doesn't necessarily mean that, right? So what you have to do is you need to make sure that you get to know the amount of each of the various isotopes or various carbon isotope inside the sample that you fetch. So for example, let's assume you fetch some particular amount here We don't know how much that is, right? We don't know how much of carbon 12 is inside, carbon 13 inside. But then if you're able to express these various components or these various isotopes in the various relatively to the others, right, in this sample, we'll call that relative abundance. Relative abundance. So that's where the definition relative abundance comes in. Relative because we are comparing with the other isotopes. We are all carbon, all right? We are in the same family. When we fetch us, we don't know how many of carbon 12 here, so we call it relative abundance. That's what the definition of relative abundance is. So relative abundance is basically the different amount of the various isotopes inside a sample of an element. So if you fetch a sample of an element, the various amount of each isotope, the various amount of the isotopes, the various amounts of the isotopes in that sample is what we call the relative abundance. How abundant a particular isotope of the element is inside the sample. So I'll go again. If I have a sample that we fetch is powder, right? So we fetch a sample of powder, we don't know how much. Let's say this is carbon again. So this particular sample contains carbon 12, contains carbon 13, contains carbon 14. And this is all that is here. But if you know the amount of this guy compared to everything, and you know the amount of this guy and the amount of this guy separated in this sample, right? The various amounts of each substance, right, is called relative abundance, right? So now, but this relative abundance, we express them in two ways, either as a percentage or we express it as a fraction. If you express the amount as a percentage, that's what we call percentage abundance. So that's what percentage abundance comes in. Percentage abundance. If it is a fraction, then we call it fractional abundance. That's it. That's it. So what is relative abundance? Relative abundance is the what? Different amount of the various isotopes in a sample of an element. Different amount of each. Relative abundance is the different amount of each isotopes. The different amount of isotopes in a sample of an element, right? Expressed as a percentage or fraction. You can either express it as a percentage or a fraction. What is relative abundance? Relative abundance is the different amount of the various isotopes in a sample of an element expressed as a percentage or fraction. What is percentage abundance? Percentage abundance is the different amount of isotopes in a sample of an element expressed as a percentage. What is fractional abundance? Fractional abundance is the different amounts of the various isotopes in a sample of an element expressed as a fraction, right? But if they ask what's relative abundance, so that's the total. You need to encompass it. Either it can be expressed as a percentage or as a fraction. That's what relative abundance is, which you really need to know, because mass spectrometry really based on that, trying to use the various amounts in order to calculate the total mass of the entire sample, the entire element that you have. So you can use mass spectrometer to be able to gauge the weight of the entire, the relative weight of a particular element in total, right? Yes. That's what we'll be looking at in the next section, right? But right now, we want to understand what relative abundance is, right? Abundance, how abundant a particular sample is relative to the others. As simple as that, you can express it as a percentage or express it as a fraction. Let's meet in the next session and look at how we are going to use this in doing various calculations.